Galileo Galilei, father of modern science. Galileo Galilei was an Italian physicist, mathematician, astronomer, and philosopher, and one of the pioneers of the scientific method. Galileo overturned the Aristotelian worldview according to which the world can be explained primarily through logic. For example, Aristotle had claimed that the velocity of falling bodies is relative to their weight. Logically, even intuitively, that might sound right. But by putting this hypothesis to test, Galileo proved that all objects fall at the same rate of acceleration. Aristotle claimed that falling objects maintain a constant speed. Galileo proved that speed increases in proportion to the distance of the fall. Galileo also refuted the popular Aristotelian belief that Earth is fixed in the center of the universe, while the stars and planets are metaphysical beings that revolved around it. This is known as geocentrism. By means of his improved telescope, Galileo was able to discover 4 of Jupiter's moons, thus proving that celestial objects can orbit something other than the Earth. And the craters he discovered on the moon's surface refuted Aristotle's belief in the metaphysical nature of the heavens. Galileo then concluded that laws of physics apply equally throughout the universe. Galileo's discoveries confirmed the heliocentric model first put forward by Polish mathematician and astronomer Nicolaus Copernicus, which argued that despite appearances, the sun neither rises nor sets. It is the Earth that is orbiting the sun.
Hey everyone. So, when I saw that video, I almost fell out of my chair because I have given that exact same lecture probably 120 times. The Aristotelian view that Galileo overturned. The thing is, the video did it much, much better than I could have. And it was only 1.5 minutes long. So, Galileo, what else to say? We'll come back to him later. He plays a large role in the history of mechanics and physics. What I can say for now is that he was the first one to put forward the idea that all bodies in the absence of air resistance accelerate at the same rate due to gravity. He didn't call it gravity, though. He didn't know what was going on at that point. That's for a future character. For now, to go to another source, we're going to go to Brian Cox, who is going to be in the world's largest vacuum chamber for a simple experiment. Stay tuned.
This is NASA's Space Power Facility near Cleveland, Ohio, and it is the world's biggest vacuum chamber. It's used to test spacecraft in the conditions of outer space, and it does that by pumping out the 30 tons of air in this chamber until there are about 2 grams left. And it's kind of got an eccentric construction, which is part of its history. It was built in the 1960s as a nuclear test facility to test nuclear propulsion systems. And that meant that they built it out of aluminium to make the radiation easier to deal with. Aluminium is not the best thing, the strongest material to build a vacuum chamber out of. So they built an outer concrete skin, which is part radiation shielding and part an external pressure vessel. So this thing can take the force that's present on the outside when it's pumped out to the conditions of outer space. Galileo's experiment was simple. He took a heavy object and a light one and dropped them at the same time to see which fell fastest. Now in this case, the feathers fell to the ground at a slower rate than the bowling ball because of air resistance. So, in order to see the true nature of gravity, we have to remove the air. It It takes 3 hours to pump out the 800,000 cubic feet of air from the chamber.
Okay, we dropped 2 millitorr in the last 30 minutes.
But once it's complete, there's a near perfect vacuum inside.
6104 manual, 10% open. Station 1, go for drop. PCV 30-1, pressure set point at 240 psi. We are go for drop.
10, 9, 8, 7, 6, 5, 4. Cameras on. 2, 1. Release.
Look at that.
They came down exactly the same. Wow.
Look.
Watch right there. Look at how they hit right there.
Exactly.
You're back on the side.
Exactly the same.
Feathers don't move, nothing.
Look at that. That's just brilliant. Isaac Newton would say that the ball and the feather fall because there's a force pulling them down. Gravity.
Hey guys, so what do you think? If I had that accent, could I have done something bigger, better? I think so too. I don't think it's just the accent though. I think if I had the Brian Cox haircut, I think I could have been a contender. But instead I'm here talking to you guys about connecting graphs of motion and acceleration due to gravity. Actually, wait a minute. I'm making this sound depressing. This is a great day. What we're going to be able to do is we're going to be able to tie together the terrific trio formulas that we have talked about and the graphs that are produced by the acceleration due to gravity. That's a great day. So if you don't already have it out in front of you, I need you to find that piece of paper in the packet titled Introduction to the Acceleration Due to Gravity. Because while it's fun to watch a YouTube video and it's relaxing and you can chill, you're not really learning all that much. Here, if we can tie it all together, maybe it'll stick. So, previously, we did some math where we derived the terrific trio formulas, starting with some basic information, and we ended up with the big three: Larry Bird, Robert Parrish, Kevin McHale. Or, if you didn't follow the 1986 Celtics, we've got our three terrific trio formulas. Now back to Galileo. What Galileo said, his hypothesis, circa 1600, was that all objects near the surface of the Earth, in the absence of air resistance, will accelerate at a rate of 9.8 meters per second squared, independent of the mass of that object. This value is so important to kinematics that it is given its own symbol, G. You've known about things falling forever, but the insights that he had, first of all, was that it's the air resistance that causes different shaped or massed objects to fall at different rates. And second, the rate that it would fall in the absence of air resistance is independent of the mass of that object. And he experimentally measured that value to be 9.8 meters per second squared. Cool? That is known as Galileo's hypothesis. So if you could, write down Galileo's hypothesis right there. It's just something you should know. Now, what I would like to do is to try to connect terrific trio, this new value for G, and graphs all together. So it says, please fill in the following chart for an object that is in free fall and traveling in the absence of air resistance, just like in the video we just saw about the ball and the feather falling. For this problem, let us assume that the object started at rest, down is the positive direction, and that G is 9.8 meters per second squared. So probably the most important thing right now is that I have to define which direction is positive. And I'm going to let down be positive. All right, so let's do this. If I want to find the velocity at any time t, let's look at what information that I have given in the problem. So if I make my chart, just like all those terrific trio problems we were doing, V naught, V, D, A, and T. Good. So what is the initial velocity? Right, it's 0 if it starts at rest. The final velocity, that's what we're looking for. The displacement is not really what we're looking for yet, so I'm going to skip that. The acceleration is downwards, so I'm going to make that 9.8 meters per second squared. And the time, well, the time's going to be a series of integers, 0, 1, 2, 3, ... Cool? So which one of our terrific trio formulas would allow us to solve for V given those pieces of information? Yeah, that's right, the first one. So let's do that. If I have V equals V naught plus AT, it's already solved for the variable, so that's nice and easy. I can cross off V naught because that is 0. And then all I have to do is plug in some numbers. So V equals 9.8 times 1. That's right. Nice job, guys. 9.8 meters per second. V equals 9.8 times 2. Again, well done. 19.6 meters per second. Yeah? All right, let's fill in the chart. So for velocity, I'm going to have 9.8, 19.6. What's the next one? 29.4, 39.2, and finally 49.0. How did I know all of those? Turns out I'm wicked smart. Actually, no, I've done those a lot. Are you okay writing those numbers down? Good. All right. So now let's find the displacement at each second. So after 1 second, what is the displacement? After 2 seconds. In order to do that, I think I can go right to the third formula. I don't mean to insult you guys, so let's pick up the pace. D equals V naught T plus 1/2 AT squared. Now, if the initial velocity is 0, what is 0 times anything? Yeah, that's right, 0. Good. So D, I can write it as just 1/2 A T squared, which in this case would be 1/2 times 9.8 times 1 squared. And all I'm squaring is the 1. I'm sure you got that from before. So it's going to be 4.9 meters. Now, with my calculator out, I'm going to do 4.9 times 2 squared. 19.6. $44.1. Now you guys can sit back and relax. If you were in class, I'd be heckling you to take out your calculators. But it's okay. Sit back and relax for a second. Pretty sure the last one's 122.5. Is that right? I can't hear you. I think it's right. So, we just used our acceleration due to gravity. We used the fact that down is positive, and we used our terrific trio formulas to plug in and solve for some values. Now let's graph it, because this is the part I want to make the final connection. Now, I went ahead and I broke up the axes appropriately. For time, I think you can skip every 2 lines could be equal to 1 second. For position, I made every line equal to 10. And for velocity, I made every line equal to 5. But you know what? I think you should pause it right now. Come on, pause it. and get the graph set up. Ready? Pause. You're back. All right. So apparently you've got the axis set. So now what we need to do is to plot those points. Let's do the position graph first. So if I'm looking at my position graph, my first data point is 0. Well, that's pretty easy. My position now. Ooh. The displacement from 0, if we start at position 0, those two things are going to be synonyms. I'm using that purposefully because sometimes a graph will be position versus time when it's the same thing as displacement versus time if we're starting at 0, okay? So after 1 second, you've traveled 4.9 meters. After 2 seconds, it's 19.6. This does not have to be perfect. 44.1. The next one's going to be 78.4. And finally, 122.5, which is like just above the top, maybe. Am I going too fast? Maybe. You can always pause it. You can. I promise. Now, if that's my graph, I know that you guys see that that does not give me a linear relationship. And that makes perfect sense because the object is accelerating. So if it's accelerating, it's going to give me that beautiful parabola, right? It's definitely a parabolic curve. And that came from a formula, d equals 1/2 a t squared, since the initial velocity was 0. Now, what that means is that that parabola, the equation is really d equals 4.9 t squared. Yeah? Yeah. Good. Cool. Let's look at the velocity graph together. This one is obviously going to be a little more straightforward. If I go and plot those points, again, it doesn't have to be perfect, but I'm going to have 0. Now, because this is a beautiful linear relationship, I'm going to draw in a line of best fit. See how it's all coming together? What would the slope of that line be? Huh? Maybe we should look at the formula for it first. The formula, well, first of all, it's linear. How we obtained that data was using V equals A T. So now, think of it in terms of Y equals MX plus B form. What was my y-axis in this graph? That's right, V. What was the x-axis? Yeah, that's right, time. The slope is going to be equal to the acceleration. And my y-intercept is going to be my initial velocity. Look at that. That's the same formula. That's what we used. It's just that the initial velocity was 0. So the slope of this line is clearly going to be 9.8 meters per second squared, which is equal to the acceleration. But I want to go one step further. Ready? What displacement occurred during this time interval from 0 to 5 seconds? Well, I know if I look over here, it went 122.5 meters. And I can see that's the total displacement on the graph. But if I was just given the velocity graph, I could also find the displacement another way, which we talked about in that graph matching activity. I could find the area under the curve. Because displacement, after all, is just velocity times time. But because the velocity is changing, instead, what I'm going to have to use is the area under the curve. So it has a triangular shape. So let's look at that. So D equals 1/2 times my change in volume, change in velocity, times my change in time. That 1/2 came from the triangle shape that we're finding the area under the curve of. So if I have 1/2 times 50 times 5, what do you get? Yeah, that's right. You get 122.5 meters. It works. The area under the curve is equal to the displacement. Okay. Still with me? All right. So I already just sort of alluded to this. Two of these formulas can also easily be written as functions of time. Now, when we have been writing out the formulas so far to date, we've been writing them as velocity equals v naught plus at. But you guys know that you could write it as a function, as in the velocity as a function of time. In our algebra-based class, we don't often write it as vt because it looks like multiplied by, but I know that you know we could write it as a function of time. Okay, I'm going to let that go. Let's take a look at the next one. I'm going to try to get through it quickly enough. I might just give you some data. It says below, please, this time, please fill in the following chart for an object that is in free fall and traveling in the absence of air resistance. For this problem, let us assume that the object started with an initial velocity of 20 meters per second up, and that up is the positive direction, and that g is negative 10 meters per second squared. So it looks like we're taking g and we're rounding slightly, but we're also going to make up positive. Therefore, since gravity always pulls it down, g would be negative. So if up is positive, let's take a look at solving for the velocity at different points. So it has an initial velocity of 20 in the upwards direction. Okay. It has a final velocity that we're going to find. The displacement doesn't matter. The acceleration is negative 10 and the time is 0, 1, 2, 3, 4. So if I utilize my terrific trio formula of velocity equals v naught plus at, I'm going to have 20 plus a negative 10 times 1. And what do you get? Yeah, that's right. You get 10. What about after 2 seconds? What would the velocity be? Good. 0. After 3 seconds? Negative 10. After 4 seconds? Negative. Oh, you're seeing the pattern. Because it's speeding up or accelerating in the negative direction. 10 just makes it easier to work with. Define the displacement. If I use d equals v naught t plus 1/2 at squared, I'm going to have d equals 20 times 1 plus 1/2 times negative 10 times 1 squared. So if I were to do that really quick in my head, after 1 second, what would the displacement be? Yeah, that's right. It would be 15. 20 minus 5, check. Given that, given those values, can you take a moment? Take a moment and push pause. Freeze the screen and plot those points. Good, thanks. All right, so if we could, let's plot some points. So for position, if I look at my position or my displacement versus time graph, if we start with the displacement or position at 0, after 1 second, we're going to be at 15 meters per second squared. After 2, it'll be at 20, 15, 0, and negative 25. Now, when I look at that, I know that you see a beautifully inverted parabola. It's nice, isn't it? Which makes perfect sense because the formula we used was d equals 20 times t minus 5t squared. If I wanted to write it in math class at this point, you would probably write it as minus 5t plus 20t. And I could throw in that plus 0, but we know it's there. Yeah? Cool. All right. All right. Let's check out the other graph. I'm going to end up with... should be a nice linear relationship. The slope of that line is going to be the acceleration. So the slope is going to be negative 10 meters per second squared. And if I wanted to, I could find the displacement, which would be the area under the curve. This would be a positive displacement. Yeah, this would be positive underneath here. And down here, we would have a negative displacement. So we could solve for what those are independently first. So my first displacement from 0 to 2 seconds would be the area under that curve. So 1/2 times 20 times 2, or 20 meters. The area under this curve would be 1/2 times negative 30. I'm sorry, my bad. Is it negative 30 or 25? Shoot! I don't know. And I've worked so hard to get here. Oh, it's negative 25. All right. Moving on. All spring, I would get all the way through a video and then screw up in the last 5 seconds. And then I wouldn't be able to edit it. Oh, God, it was brutal. It was brutal. Now, this is when I would normally turn to the class and say, all right, guys, what did I do wrong? What did I do wrong? Someone yell it out to me. Oh, it was 30. It was 30. So this would be negative 45. That's right. Nice job, everybody. So my change in displacement overall will be plus 20 minus 45. So the total displacement over that interval would be negative 25 meters. Check, check. Phew. Again, I thought physics was collapsing right before your eyes. I'm not sure what I'm going to edit out of that. It might be substantial. You guys still there? All right, this is what we did. We tied together graphs of motion, Galileo's hypothesis, and the terrific trio formulas. We use the formulas to come up with the data to give us the graphs. The graphs tie back into what we talked about at the beginning of the year. And it really it ties into so much of what you've done in math class over the years. Whew. If you were able to hang in there for all of that, good for you. You're going places. All right, that's it for now. Whew. Don't burn this paper. Hang in there, and we'll talk soon.